nuclear energy technology. So we've been talking about fission when you split large nuclei. How about fusion? We see that it works very well with the sun, and it works for hydrogen bombs. But what about controlled fusion? Well, what is fusion? Here we show a DT reaction, deuterium and tritium. Deuterium has one proton and one neutron, so it is heavy hydrogen. So it's identical to hydrogen, except it has one neutron and is heavier. Tritium is doubly heavy hydrogen. You have one proton and two neutrons. The highest reaction cross-section, the most likely way to get fusion, is between deuterium and tritium. So this is a reaction that we're working with. How do you get these to fuse when they're both positively charged? You're going to need a lot of kinetic energy for them to overcome the electrical repulsion of being positively charged and run into each other to fuse. So it's got to be very hot. You need them close together so they'll be likely to fuse, so it's got to be very dense. So the first way to make this work was to compress and heat them with a fission bomb, basically greatly increasing the explosion that you could get with a nuclear fission bomb. And so we can see their attributes are they are very aesthetically pleasing, but they're not very controlled. In order to have controlled fusion reactions, we're going to need a way to confine the fusion plasma. What's plasma anyway? So we all know that there's three states of matter, solid, liquid, and if you add more heat to a liquid, they overcome their bonds and you have a gas. But if you add more heat to the gas, the electrons are no longer bound to the nuclei and freely move with great energy. So maybe you've heard that the sun is a burning ball of gas, but in fact, it's a fusing ball of plasma. So how do we confine this plasma? The sun does it fine because it's huge and the gravitational field pulls it all together. But these charged particles with great energy, anything they touch, they will react with, and they'll lose all their energy. So there's no way to keep the energy and to keep the plasma inside of a vessel. However, charged particles will not cross magnetic field lines. So if you have a magnetic field, the charged particles spiral around them. So this confines them very good in this perpendicular direction, but they can move along the parallel direction, and they do. So how do we confine them in this direction? What we do is we take the magnetic field lines and we bend them into a circle, so we have a big donut or a big bagel. This shape is called a torus. And so we have a strong magnetic field that goes in a circle. We put a plasma in the middle, and we put a chamber around it. So what you're looking at here are the magnetic field coils that make the magnetic field, the plasma on the inside. But what we don't show you is the vacuum chamber, which just looks like a big bagel that goes around this and keeps a very high vacuum in here because you don't want anything except your deuterium and your tritium. So the challenges are, the first challenge is we have to maintain a very good vacuum. That's very expensive technologies. Then we have to stabilize the plasma because with all this energy, the plasma can break through the field lines and hit the wall of your chamber. And then you have first wall interactions that spread all these impurities in your plasma and contaminate it. And then it won't fuse anymore. Throughout the more than half a century that we've been working on this project, we've made profound progress toward fusion. At the same time, there's still much yet to be done. And it's been often said that fusion is the energy of the future and will always be. So what's the problem? Well, the bottom line is we can make it work. We have the technology. It just costs a lot of money. If we compare it, for instance, with the fission reactor, here you have a bunch of radioactive stuff sitting in a hole, getting hot, boiling water. So with fusion, what's different? Well, the big thing is you need to maintain a good vacuum vessel. You also need some of the highest magnetic fields we've ever produced in a laboratory. And so this is a very sophisticated piece of electronic high vacuum experiment. Furthermore, once you start to use it, it's radioactive, and if something's broken, you can't go in there and fix it. So it's not that we can't make this work. It's just not going to be cheap. There's a great fusion reactor out in space there called the Sun that produces a huge amount of energy that comes to us that we can collect with solar panels. And we can do it much cheaper with this solar collector than we can with the fusion reactor in a laboratory at present. So the last thing we could look at is National Ignition Facility. This is an inertial confinement fusion, which amounts to little hydrogen bombs at Lawrence Livermore Laboratories in California. So the idea is, if we can make hydrogen bombs work, how about if we just make them real tiny, and rather than igniting them with a fission bomb, we blast them with a very powerful short laser pulse that will compress them and heat them, and they'll explode. They'll explode inside of a large sphere, and we will cool the wall of that sphere with water that will boil to generate electricity. This may be an energy project in name only. Weapons research is a significant portion of the motivation for the project because it allows us to both study fusion explosions and how to make very powerful lasers. So there you go, some of the technology regarding nuclear energy.